Now let's start talking about Young's double slit experiment. Young start using a light from one source and he used a single slit here, and the light then passed through double slits. Why Young's make this? To make the light coherent, make the light come from the same source, okay? So the light is coherent, same frequency, same wavelength, and same amplitude. And he see what happened on the screen here. He find that there is a light or bright pattern and dark pattern on the screen, okay? The dark and bright points coming from monochromatic light source. It is the light of one color or one wavelength and one frequency. We have here the bright fringe and here a dark fringe, another bright fringe, and so on. As we mentioned last class, we said that we have here bright, then here we have dark, bright, dark, and so on. Okay? Now, the place where you have a bright fringe, there is a constructive interference. Okay, here the sources of light, and this is light number one and light number two. The phase difference is zero, path difference is zero, so we have bright fringe. Here we have two rays. The difference between these is lambda over 2. This ray move more than the other one for lambda over 2, so we have a destructive interference. We have a dark fringe. Again here we have another bright fringe. Why? Because the distance traveled by this light is lambda. So if the difference in the path between the two sources is 0 or lambda, we have, or 2 lambda, we have constructive interference. And if the difference is lambda over 2, 3 lambda over 2, and so on, we have a destructive interference. Okay, we have here bright fringes are seen where constructive interference occurs. That is where the path difference between the two diffracted waves from the source A and B is n multiplied by lambda, where n is a whole number or integer number. Dark fringes are seen where destructive interference occurs. The condition for dark fringe is that the path difference should be n plus 1/2 multiplied by lambda. Okay. Again, let's make a new figure. This is the screen where the fringe is seen, and here we have the two sources of light. The distance between the two slits here is small a. This is the symbol for it. The distance between screen and the point of the slits is capital D, and here we have the bright, here the dark, another bright, another dark. The distance between the central bright and the first bright, or the center of the first bright, is x. The distance between the center of the central bright and the second bright is 2x. Okay, since this distance equal to this, and the distance between the dark is equal as well. Okay, so we have a relation between the distance of the first bright from the central bright, it's equal lambda multiplied by d, the distance between screen and the slits, over a, which is the distance between the two slits. If we take the position or the distance for the second fringe, 2x, so we have to multiply it here by 2. If you're given the distance between the central bright and the second bright, so we have 2x. You may divide by 2, the distance by 2, to back to your relation, which is x equal lambda d over a, or if you take here the total distance, which is from here to here, you multiply it by 2. Now, if you're given the distance between the central bright and the first dark, this distance is x over 2. So you have to multiply this by 2 and put it here. So x تساوي lambda d over a. In this way you can find the value of the wavelength. Calculate the observed fringe width for young double slit experiment using a light of wavelength 600 multiplied by 10 to the negative 9 and the slits 0.5 times 10 to the negative 3 meter. This is A. The distance from the slit to the screen is 0.8 meter, so you can find the value easily. Now, although Young's original double slit experiment was carried out with light, the conditions of constructive and destructive interference apply for any two-source situation. The same formula applies for all types of waves, including sound, water, microwaves, provided that fringes are detected at distance of many wavelengths from the two sources. Sometimes when you use the microwave, you can see that some places in the food is hotter than another places. Why is this? Because the constructive and destructive interference. If we have this is ray number 1 and here ray number 2, maybe this ray move distance longer than this by lambda over 2, so we have a destructive interference. But if they met by a difference of lambda or n lambda, and n is integer, so we have a constructive interference and the food will be hot. Now we wanted to talk about stationary waves. Stationary waves is very important in devices or in musical instruments. The wave pattern on the vibrating string is called stationary wave or standing wave. Okay? The waves in the air which carry the sound to our ears transfer energy and are therefore called progressive waves. Stationary waves are trapping energy. They will not transfer energy from one place to another. So this is the difference between stationary and a progressive wave. Okay? Stationary wave is the result of interference between two waves of equal frequency and amplitude traveling along the same line with the same speed but in opposite direction. So if we have string like this and you pluck it here, it will start to move up and down. So we have a standing wave here. Okay, this is a type of standing wave. You can see this string just moving up and down. Okay, or you may see like this. Okay, moving up and down. This will move up and the upper part will move down, or maybe like this. All of this is a standing wave. Okay, all of these are a standing wave. we have two waves from different directions, opposite direction, but they have same amplitude, same frequency, and same wavelength. Okay, so we have a standing or a stationary wave happen in this place. Okay, stationary waves on a string. If a string is plucked and allowed to vibrate freely, there are certain frequencies at which it will vibrate. The amplitude of vibration at these frequencies is large. This is known as resonance effect. Okay, so the resonance effect when the amplitude of vibration at these frequencies is large. It is possible to investigate stationary wave in a more controlled manner using a length of string under tension and vibrator. Now, in this figure, we have a stationary wave or a standing wave. This is called the fundamental mood vibration, okay, or the first harmonic. At the ends of the string, we have here the nodes and we have an anti-node, okay? So at the center, we have the anti-nodes, and on the sides, we have nodes. Nodes and antinodes do not move along the string, okay? They will stay at their position. Now, if this distance from here to here is the length of the string, and this string makes half wavelength, so the wavelength of this string equal to 2 multiplied by L, okay? 2L. The wavelength lambda of a standing wave in the fundamental mode is 2L. Okay, this is the first harmonic or fundamental mode. The wavelength is 2L. What about the second harmonic? Okay, this is the second harmonic. You can see that the length equal wavelength because we have 3 nodes and 2 anti-nodes. This is anti-node and this is anti-node. So here the wavelength equal L. This is the second harmonic. In the third harmonic, this is the wire or the string. Its length is L. We have lambda and a half. So L equal 3 lambda over 2. So 2L equal 3 lambda and lambda equals 2L over 3. So the third harmonic is 2L over 3 and so on. You can find the value of the frequency if you know the value of the wavelength because V equals lambda by frequency. So frequency equals V over lambda and V equals speed of light if the object moves in the speed of light. So here we have C over lambda equal frequency. So for the first harmonic, it's C over 2L. Here C over L, C over 2L over 3. Okay, or we can make this relation frequency equals NC over 2L. For the first harmonic, it is C over 2L. For the second harmonic, 2 with 2, C over L. For the third harmonic, 3C over 2L, 3C over 2L. It's the same. Here we have stationary wave explained by interference. At the beginning, the wave starts from the top at time equals 0. Okay, we have two waves, one from this side and the other from the other side. Okay, we have mainly two waves. This is wave number 1 from left to right, and we have other wave from right to left. So we have a constructive interference. This is the total wave. Okay, this is at time equal 0. After a time of 1 over 4 of the period, quarter of the period, the waves come from different directions. But what happened that this is the wave number 1 from left, and this is the other wave from the right. They are moving in opposite directions, and there is a phase difference between these. It's about 180, so they cancel each other. So at the beginning you see wave like this, and you see then this line. After you see this shape here, you back to see the line, and back to see the same shape. 1, 2, 3, 4, 5. Okay, here instead of the waves in the upper side, they are in the lower side. So we have this total at time equal to t over 2, which is half the period. At 3/4 of the period, they back to the same shape as time t over 4, and it's back again. Okay, this is the stationary wave. You can see many videos about stationary waves to understand it better. Okay, stationary waves in air. Here we have a speaker and closed side, and if we have a sound, the sound will hit this closed side and back. So we have two waves in opposite direction, same wavelength, same frequency. So we may have a stationary wave. We will change the frequency here till we get a stationary wave. Here, as you see, in this stationary wave, here start by a node, and here end by an antinode, here antinode, node, and so on. Okay, we have many types of open end tube or a closed end tube. Okay, now for a stationary wave in enclosed pipe, the air cannot move at the closed end, and so this must always be a node. However, the open end is position of maximum disturbance, and this is an anti-node. Okay, so from one side it is open, from the other side it's closed. So we have a wave like this. Here we have node, and here we have an anti-node like this. This is a closed pipe or closed end. Node, node, antinode. The distance between these two nodes is lambda over 2, okay, and this is lambda over 4. So this distance is 3 lambda over 4. So the length of the tube is 3 lambda over 4. This is not the first harmonic, this is the first harmonic. This is the first wave you can see, okay? This is the second mode of vibration, okay? And this is the third mode of vibration. Let's draw this shape. Starting, this is an open end, another one, another one, okay? And here, okay. Now, here L equals lambda over 4. Here L equals 3 lambda over 4. Here L, which is the length of the tube, equals 5 lambda over 4. Okay, as you see here, this is a quarter of wavelength. The general expression for a frequency of the nth mode of vibration of the air in the closed tube, the nth harmonic or the n minus 1 overtone is Fn equals 2n minus 1 over 4Lc. Here we have the first and second and the third harmonic frequency. Okay, how can I find the frequency? Using the relation V equals lambda multiplied by frequency. Speed is constant, so the frequency equals speed over wavelength, and the wavelength here equal 4L. You have to remember these values very well. You will be asked to calculate the first or second or third harmonic. Okay? Stationary waves using microwave, same thing. Here we have a wave and it's hit a reflector and it is back. While it's moving back, there is another wave from the microwave source, so we have an interference here. So maybe you have in constructive and destructive places, you can move this probe from place to another to see where you have an antinode and where you have anodes. Okay, when you have a node, there is a quiet sound. When you have an antinode, you have a very high sound. Measuring the speed of sound using stationary waves, as we mentioned before. Here we have a tube, big tube full of water, and we have a tuning fork. We make the first signal and start moving this tube up, okay? So the empty space increases. At the beginning, maybe we have the first harmonic, and when you move it more and more, you will hear the sound again. Okay, here we have a big sound and then slow sound, and then when you hear the same sound again, which is a big one, you can recognize that you have the second harmonic. Okay, so you can, by using this way, calculate the speed of sound. Okay. Now, finally, we have to talk about diffraction. Diffraction happens when the wave passes through a gap or when it's hit an obstacle. If we have a wave like this, and after an obstacle like this mountain, we have this type of wave. So the diffraction is the movement of the wave through an obstacle or through a gap or bend from an obstacle. Okay, we have a difference between small gap and larger gap. If the gap almost equal the wavelength, so we have circular diffracted wave, and if the gap is larger than the wavelength, we have almost square wave. The wavelength is the same before and after in both cases. Frequency is the same in both cases, okay? And the speed is the same as well. Diffraction is defined as the spreading of the wave into a region where it would not be seen if it is moved only straight line after passing through narrow slit or past an edge. Okay. The greatest effect occur when the wavelength is about the same size as the aperture. Okay, the wavelength of light very small. Green light wave has a wavelength of 5 times 10 to the negative 7, and therefore diffracted effect can be difficult to detect. Okay, so depending on the gap, you can see the diffraction better way or in a bad way. Okay, what is the Huygens explanation of diffraction? Huygens said that if we have a wave, each point on the circular wave is a starting point of a new wave. So we take the crests together to form a new wave, and so on. Here we have a new waves, and this is the new waves. Okay, so Huygens said that each point in the wave is a starting point to the other wave. Okay. He suggested that at any instant, all points on the wavefront could be regarded as a secondary disturbance, giving rise to their own outward spreading circular waves. Okay, this is a diffraction of light by a single slit. If we have a single slit, we may have a shape like this. Okay, this single slit diffraction pattern has many features that we associated with an interference pattern, but how can a single slit produce the interference type pattern? This is a question in an external exam. Okay, the explanation that follow is based on Huygens wavelength or wavelet idea. In the figure shows planes wave front arriving at a single slit at width A, each point on the wavefront passing through the slit can be considered to be a source of a secondary wave. Okay, what is the law used for a single slit? The law is sine theta equals lambda over A. Okay, lambda is the wavelength, A is the width of this slit, sine theta, it is the angle of the ray pass through the gap. Okay, it's very important law. And sine theta equals n lambda over A. This is the condition to observe the first dark fringe at angle theta more generally. And because the angle is very small, so sine theta equals almost theta, so theta equals n lambda over A. N is the order, lambda wavelength, and A is the size of the gap. The diffraction grating. Diffraction grating, it consists of a piece, consists of maybe 10,000 small gap, okay? We call these grooves, okay? As 10,000 slits. Now, what we will see on the screen, we will see the same thing as in double slit, but the distances are not the same as in the slit, okay? The distances are not the same as in the Young's double slit. We may have here the central bright, okay, this is the slit, this is the central bright, this is the first bright, the second bright may be here, okay, and this these are make an angle like this. We have we put a screen which is in a circular shape, okay, so this angle is not equal to this angle, okay. Now what we will have here on the screen, we have, as I said, here is the bright, 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 and bright on the both sides, okay. This is the 0th order bright, this is the first order, second order, third order, and so on. Now, what is the law used for calculating the values? It's d sine theta equals n multiplied by lambda. What is d? D equal the length of this piece, which is the diffraction grating, divided by number of slits in it. So if it's given for you by 10,000 slits and 1 millimeter, you divide 1 millimeter by 10,000. Sine theta, it is the angle between the 0th order and the bright fringe, which you want to find the angle or whatever. So if you asked to find the distance or the angle of first, this is theta. Second, this is theta, okay? So d sine theta, d, it is the length divide the number of grooves. This is sine theta, it is the angle of the order. You take the first order, you take the angle of the first order. Lambda is the wavelength. If he asked you to find the total number of fringes that can be constructed, so you have to take the angle to be 90 degree, and sine 90 is 1. Here we have the 0th order, first, second, and third order. If the first order at 10 degree, the second order may be at 21 degree, and the third order may be 52 degree. So the angles are not the same and are not depend on each other. Here we have an example, monochromatic light with 7 times 10 to the power 5 lines per meter. So D equal 1 over 7 multiplied by 10 to the power 5. This is D. A second order, so N equal 2, is observed at an angle. This is the angle. Calculate the wavelength. Very easy. D sine theta equals N lambda, N2, angle given. D is calculated here, so you can find the value of the wavelength. We use here a monochromatic light, which is red or blue color or whatever. What if I use a white light instead, and the white light pass through the diffraction grating? What happens is the light will pass in the 0th order as it is, white light, sorry, but on the sides, the light will split to its colors, okay, which is Roy G. Bev, and the red will be on the the red will be away from the center, okay? The violet will be closer, because this depends on the wavelength of the red and wavelength of the violet. If white light is incident on diffraction grating, each wavelength making up the white light is diffracted by different amount as described by the equation d sine theta equals n phi lambda. Red light, because it has longest wavelength in the visible spectrum, is diffracted through the largest angle, and the blue light has the shortest wavelength and diffracted the least. Okay, by this we finish the waves. You have to study harder and solve many questions about the waves. Next time, inshallah, we will start with the electric field. Assalamu alaikum.